So hello everybody, good morning. This will be our first official lesson of the course, and there will be a corresponding problem set at the end, as you'll probably be able to see where this actually there. The title of today's lecture is going to be Graphical Analysis. Now I will say that I believe this is all going to be review, not just from Math 3, but from Math 2 as well. We'll be looking at different graphs, we'll be looking at their behavior and describing their behavior, and translating that description into the x values on which it occurs. So it's going to be a little bit familiar, but at the end you'll start to see how we might push this a little bit forward and ask you some questions that are very concrete and visual in some ways that are going to feel a little bit more abstract and uncomfortable. So you'll get a sense of that kind of, I want to say almost transition that we've been talking about, and moving from things that you know to some versions of those things that might be a little bit more challenging and tricky. So having said that, up on the screen right now is included like all the essential information for our day. We've got the notes, number, and title. I would encourage you to include those in your notes to keep them organized. I think it will help a little bit. The dates there as well. I have an essential question, which in our case is kind of like the learning objective, just kind of phrased into a question. It's not always perfect, but it's fairly close. Today we're going to focus on answering the question, what is interval notation? How do we use it? And how do we visually determine domain, range, and the positive, negative, increasing, and decreasing intervals, presumably for a function? So that's where we're going to begin, is interval notation, and then we'll move into that other piece. And I'm going to move pretty fast. I'm going to hopefully have some resources available for you if you'd like to not just sketch them out, but kind of print them out and attach them into your notebook later. But unfortunately, that's one of the toughest things about what we have going here. So I'll do the best I can. And as mentioned, without further ado, let's begin. So to kick things off, I just want to kind of establish some vocabulary for these things. Again, you probably haven't been doing a ton of math over the summer. If you have, kudos. I'm glad to hear that. But I understand that not every person's probably going to be doing that, and that's okay. So where I wanted to start with is something that's very grounded in work that you've done in math probably since elementary school, and that is inequalities. So inequalities are a way of comparing two values, and in particular describing a whole set of numbers that allow you to compare. So for instance, one such inequality might be x greater than or equal to 4. And we know that this kind of translates to all the x values that are larger than 4. And in order to do that without having to describe it in so many words, we'll oftentimes draw a number line and kind of shade in where those areas are. So in this case, we might put 4 at our center. We'd put an open dot because we're not including 4. We're saying strictly greater than 4. And then to say that all the values are bigger, we would shade it in. Or if you prefer, I've seen people do this as well. Neither notation is incorrect. It's completely up to you and dependent on what you've done before. So there would be one such inequality. Now, of course, we could go in the other direction. We could talk about x being less than or equal to 7. Should have had some number lines ready. In this case, we'd have 7 in the center. Because we have that or equal to, we would be including 7. So we shade in that circle to indicate that we are including 7. This is inclusive. And then we want the values of x that are smaller. So that would be all the variable values that are to the left. So there would be one such inequality. Finally, there are two other, I guess finally wouldn't be appropriate if there are two others, but there are two other forms of inequalities that you might run into. So one of them would be what's called a conjunction. Let's say it's going from 3 to 11. So in this case, we'd put two different numbers down, and we're saying that the values that we're talking about, the ones that satisfy this inequality, are all values between 3 and 11, but including 11. So we'd shade in 11, and then we'd shade the values in the middle. It creates this sort of like dumbbell, or maybe some sort of smiley face sort of thing. Maybe it's like a crocodile snout of some kind. Like, I don't know, your call. We'll see how much this gets into the actual lesson tomorrow. But again, you don't need to know the name, but it's nice to just kind of remind you that this is called a conjunction. On the flip side, there are also disjunctions. So in this case, I'm going to flip this one around literally. We could have x less than or equal to 2, or x greater than 17. So in this case, once again, we have two values, 2 points of contrast, or two like limiting areas. In this case, we'd be saying we're less than or equal to 2, so we'd include 2 and shade to the left. And we would not include 17 and shade to the right. And this is called a disjunction. They're not coming together. I don't know if you know a whole lot about like word morphology, but con means with. So these two come with one another. They come together. On the other side, those guys go apart. So it is what's called a disjunction. And it's disjunction, not like dat junction. Well, that'd be pretty funny. Probably can turn that into a joke. Now, having said that, there is an alternate version of this, and it's not different. It's describing the exact same values as before, but there's an alternate notation that's here. And that would be what's called an interval. And truthfully, this definition is the same as the one that's right there, but I want to include it just to be safe. I want to always establish that we're defining things and we're working from those definitions. Although I will say that in pre-cal, we're a little bit looser with our definitions than we are in calculus. But basically, an interval will be a set of two real numbers, specifically between two numbers. So basically, in order to write a single interval, and we could, of course, write more than one, as you might remember already, but oops, should have been between two values. These are the kinds of mistakes I'm going to make tomorrow. So what we're going to do with an interval is we're going to translate it a little bit. Whereas before we said things like less than or equal to and greater than or equal to, and we talked about less than or greater than, what we're going to do is we're going to transfer those or translate those. These ones will become hard brackets or closed brackets. Both those names apply. And the ones over on the other side are going to be open brackets. The idea is open because we're not actually including that other one that's there, whereas the closed bracket is including it. It's like the door has shut and that person's inside, so now it's included in the set itself. Not a perfect analogy, but I'm doing the best that I can with what I have. Having said that, we can also then, of course, demonstrate some intervals by translating them from inequality notation. So, for instance, I might give you this inequality. This is a pretty common type of inequality. So we'll say we'll go from negative 13 to 5. Well, that's in inequality notation because we have the little gator mouths or whatever we want to call them. But as far as an interval, our interval would run from the smaller number to the bigger number. The less than one would include an open bracket or parenthesis. And then the closed bracket would be the one that includes the number itself. So there would be our version of this inequality, or this set of numbers, in interval notation. Now, going in the other direction, like normally something like x greater than 3 is like the easiest possible inequality because you just like draw the number and then pick the ones that are bigger. Here it's a little bit tough because we do say in interval notation that we need to be between two numbers. And you might look at this and go, well, there's only one number, so what am I supposed to do? And the answer is, well, fairly simple. We say that we want all the numbers that are bigger than 3, so we're going to go 3 to the biggest possible thing you can think of. Like, what would you describe the biggest possible thing you can think of numerically as? Like, what's the word for that? Yeah, I agree. It's definitely infinity. So that's exactly what we'd say. Like, this isn't a perfect way of representing it, but it does a pretty nice job. We'll say that we're going from 3 all the way up to infinity. Now, in this case, it might be tempting to include a hard bracket on the infinity, but we're not going to because infinity is more like a description of something so large that we can't get to it than it is an actual number where we're like distinctly between. So we're just going to always use a soft bracket on infinity, whereas with the 3, had there been an or equal to, we would have switched that to being a hard bracket. So keep that in mind. Last but not least, kind of the other one, I think this probably is close to ending our practice here. If we want to say something along this line, we want to include a disjunction, then in this case, what we need to do is we need to kind of look at each of those two separately. So in fact, to help me with that, I'm going to use two separate colors. We'll go green and we'll go brown. Actually, I had a student in the class of 2016 that was obsessed with the color brown. And so every time I'd go, hey, give me a color, it'd go brown. And he sat really close to my desk, so he always got it. So for x less than or equal to negative 4, we'll go from negative infinity to negative 4. And again, I'm going to negative infinity because we want all the things that are smaller. And then we'll include 4, so we'll use a hard bracket. On the next one, we want to go from 10 to the biggest thing possible because we want all the numbers that are bigger. So I'll make a soft bracket on 10 because it was just greater than 10, not greater than or equal to. We'll go to that representation of the biggest thing. Always get a soft bracket on our infinities. And then that would apparently finish everything. But keep in mind, because there are two separate intervals here that we want to consider together, we use a symbol called the union. So this little guy is called the union symbol. It says to include both of those options, and it basically translates into this, what would be the word I'm looking for there? It translates into disjunction, basically. So there is the basics of interval notation. So before we go too far, I did want to kind of throw out just a couple other pieces here, some extra vocabulary you might hear me say, and then we'll do a couple more examples and call it a day, just in this portion of the lesson. It's taking a little longer than I wanted to anyway. So first and foremost, if you have an interval that includes both open brackets on both sides, you will often call this an open interval. Seems fair because both endpoints are open, so it's all numbers between A and B, not including A or B. And I bet you can figure this out. We talked about open bracket and closed brackets before. If you have two closed brackets, like I bet you would guess that this would be called a closed interval. So basically we could have all open or all closed intervals. If you're like, what happens if there's a mixture? Well, I'm sure there's some funny names. In fact, a friend of mine was talking about Clopin that had been studying mathematics in college. But again, like we're talking about open and closed. So basically those two would be there. We don't have a fancy name that we're going to use for the other ones. So having said that, the next piece I want to do is I just want to quickly demonstrate a little bit what this is going to look like. So we're going to rewrite these in interval notation. Obviously, in a perfect world, you'd be able to practice some of this like as a triad in class, but we don't have that possibility. So we'll just kind of play with it for now. So we want to rewrite this in interval notation. Like if you wanted to think about what the homework's going to look like or your problem set for the night, it's going to include also like sketching it out. So maybe that would be helpful first to just kind of sketch this out for us. So we'll go from there to there. Next, I'm going to look at the brackets. So we have or equal to on -2. So I'm going to shade that circle in to indicate that we're including it. And then we're going to go greater than 819. So I'm going to do an open circle. And then I want the bigger numbers than 819. And x is less than or equal to -2. So we want the smaller numbers for this one. So this is what we called a disjunction earlier. As far as like the interval notation version, like we are going to include both of these two intervals. So it's like imagining that there's a negative infinity right there and imagining that there's an infinity that we're never going to touch, but at least then we've got that idea of kind of boundedness in there. And basically I'll say that this is the intervals from negative infinity to -2. And then I'd probably ask you, do I need a soft bracket or an open bracket or a closed bracket, also known as a soft bracket or a hard bracket? And you would say likely a hard bracket. On the other one, we'd go soft bracket or open bracket because of 819. And then we'd go all the way up to infinity. And then we attach these together because this is a disjunction. We want to include both of those possibilities. We include them with a union symbol. Now, I didn't include this on the previous page, but I do want to catch your attention with it. In a sense, like the picture and the intervals right now don't include what variable we're talking about here, whereas these were really nice and clear in including these x's. So for that reason, something you'll often see me do, but not necessarily going to harm you if you don't in this case, is I'm going to put that x is a member of that. So that little like sideways comb thing, that is read as the member. So it's saying that it's a part of that interval. So the x values are all included in those sets of numbers. So now from here, there are a couple other options that I got down here. So I've got one more here. I can do one more. I'll just do the interval notation part just for the sake of time. I think that's a smart move. Since it's already drawn. No, I can do both. I can do inequality. So we're looking for values of 42 that are, or values that are larger than 42. So you obviously might say that x is compared to 42. If this is open, that means it's not going to be or equal to. It's going to be just strictly greater than 42. So we'll say x is greater than 42. And then in interval notation, we'll say that we start at 42 with a soft or open bracket, and we extend up to infinity. The only thing, again, I'd include here is I'd include x, or whatever variable. Maybe we wanted to talk about y in this case. We'd say y is greater than 42, or y is a member of 42 to infinity. Last one on here is a little bit of a cheat, but it's the sort of thing that sometimes throws people. What if I give you the inequality x is equal to 17 pi? And now I would tell you that if I gave you such an inequality, you could argue back and say that's not an inequality, because there's an equal sign in there. It's literally an equality, and you would be correct. But for the sake of argument, to make sure that we cover this, the way you would do this is start it out the same way. You'd plot 17 pi in the middle of your number line. And then since it's included, we would put a closed dot there. Now we're not talking about values larger than or smaller than 17 pi. So that's it. We have now drawn this in a graphical representation. We just have that single value on the number line at 17 pi. Likewise, if you wanted to actually write this into interval notation, there are a couple different ways that would be acceptable. Again, this is a small thing, but it's there. One option would be just to use inequality notation or just to write the equality. If you wanted, though, oftentimes in intervals, people want to kind of have this idea of set membership, saying x is inside this set. Well, the set only features one item, so we'd use these curly brackets, whose name I don't actually know off the top of my head. Maybe I'll research that by tomorrow. And we say that x is a member of that particular thing. Or if you didn't want to include the x as a member of, you could just say that. That's saying it's a part of the set that only has one single number in it. And having said that, that gets us through the interval notation part. So likely, I do have a triad at the end. So if this was something of particular interest to you, I might ask you if you wanted to take a look at it. And yep, that completes our first portion of the lesson. 35 minutes left. So far, so good. Our next little piece we're going to hit are some properties. So in other words, what we started with was interval notation, so you'd be able to effectively describe things like domain and range. It was just kind of a quick review. Now we're going to talk about those properties themselves. You'll notice in some of these I've already written in the definition, and some of these I have not. In this case, I already have the definitions written. My hope is that this is a review, but at the same time, if it's not, please do ask a question and let me know. I'll looking at the chat, and I don't actually have the chat open because there's no one here, but just keep that in mind. So we're going to talk about some properties of a function or a relation. So we're going to give you some sort of set of points, like we have down at the bottom. We have an ellipse. Maybe it's a bad circle. I might have been the one drawing it. And we're going to use interval notation to represent these properties, the domain and range. So as it says in these definitions, it says that the domain of a function or relation is going to be the possible input values for the relation. And in other words, we're asking what x values are valid for that particular relationship. Like what x values are used, what x values are possible for us to see on that graph. And then likewise, the range is going to be the possible output values of a relation. And in other words, that's going to be the y values. And now this can be a little bit tricky, so I think I've developed this in a way that will kind of help us see it. But this is kind of my mindset. Like I used to use this thing called the beep test, where I'd kind of travel my cursor along and I'd be looking for graph, and if there's no graph, there's nothing, then I'd be like beep, 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 and then stop. It doesn't really work that well. It's just kind of goofy, and I don't think it helped people learn. So this is what we're going to do instead. So we're looking at this ellipse, and we want to figure out the domain and range. Before we do anything, the first thing I'd probably begin with is I'd write out my x as a member of and my y as a member of. The reason for that is we need to distinguish these two, and one quick way to convince your reader, the person who's reading your work, that you understand what domain and range mean is by making a correct connection between x and y values for the domain and range respectively. So I'll start right there, and I'll say that domain is going to be the x values and y is going to be the range, or the range is going to be the y values. Having said that, what we're really interested in are what x values are being included in here. And you can kind of see that the x values we're looking at are right there. And you can also pretty much see that the y values are happening right here. So many of you would probably be able to look at this and just instantly grab those values off the graph, and that's awesome. But if you're not, here's something that I sometimes kind of visualize. It's called projection. It's not like the psychology version. This is called mathematical projection. And it's like imagining that someone shined a really, really strong light from above or from the side, and then looking to see what x values and y values are projected, aka the shadow appears on the x and the y axis. So here's what I mean. I'm going to pretend I'm projecting this giant light on it, and I'm going to first talk about domain by shrinking this graph down to the x-axis. So there is our graph. I've just kind of projected it. In other words, we can no longer see that it's a circle. We've just kind of shoved it down onto the x-axis. As we look at that, I can see really clearly what my x values are. I'm moving between x equals -4 and x equals +2. So I'm going to undo that here really quick. So we're going from -4 to 2. Now the question might be, should this be an open interval or a closed interval, or what types of brackets should we have? There are no dots drawn in here, but it looks like it's actually like existing right there. So you kind of have to, in your mind, imagine there are gigantic like dots and points plotted at those points. In this case, we're going to use then an inclusive or a closed bracket to make sure that we include those two x values. The only way they might not be included would be something called asymptotic behavior, but we're not going to worry about asymptotic behavior for a little while, so you shouldn't have to stress about it. So likewise, let's see if we can use the same strategy for the range. So looking at our picture, I want to now see what y values are included in here, so I'm going to quote-unquote project it onto the y-axis. And again, if that word projection bothers you, don't worry about the word. I'm just using the technical terminology for it. But there allows us to see really quickly what my range is going to be. So looking at our graph, it looks like our range is going from, does that look like -4 to 4? It does. And just as we did before, just as we did before, like there's no reason to think that those values aren't included, so I'm going to use a hard bracket. So there are our domain and range, and the method I used was just crushing it, basically. It's called the projection method, like I did use what's called projection, but I basically just imagined crushing the graph down to the x or y axis to see where it actually shows up, and we can get a really good picture of what's there. So I'll do one more, and then I might be able to give you a quick little triad. I've got about 30 minutes remaining, so I feel like I'm doing okay, although again in class the pace will be totally different. I'll have way more adrenaline, but whatever. So in looking on here, we want to next figure out the domain and range of this particular function. And of course nothing's written here, so I've got a little extra work. But I'm imagining as you look at this picture, you might actually like feel a little bit more intimidated by it because there's just a lot more stuff going on. And give me 1 second, please. I'll do this. I'll have domain and range as two separate ones because then we'll be able to visualize it a little bit better. So we want to talk about domain and range. Well, remember I said something first. The first thing that we'll do when we're doing domain and range is make sure we establish the correct variables. So I'm going to use X, I'm going to use Y for domain and range respectively. We'll kick things off right there. Next, I want to see what X values are being used. And I'm going to admit, this one could be a little bit tricky. I 100% agree. So looking at this particular graph, because we've got a lot of stuff going on, like a good starting move would be to project this down to the X-axis. So you can see I'm just kind of crushing it on there. Excuse me. So looking at this picture, it would appear that our domain is going only from -4 to 4. But here's the problem. Like, this is an easy mistake to make. In reality, these arrows are giving us more information than they're actually showing on the diagram itself or the sketch. Those arrows mean continue forever. So truthfully, if I were to do this properly, what I should do is I should imagine extending the... I can't do it. Wait, I can do it. I think I can do it. I should imagine continuing these arrows out further and further in all directions. Because basically, even though we don't necessarily see it, they're just going to continue outward. Those arrows are saying continue going in that direction, and they're both going down and further to the right. So if I make this little adjustment here, again, the graph looks a little bit wonky, but now when we pull it together and kind of do our projection itself, you'll notice that, again, not perfect, but if we look at this shape, it looks like it's covering the entire x-axis. And that's actually correct. This actually does have domain of all numbers between -infinity and infinity. So remember that the arrows indicate continued behavior. So this is how you read arrows. They mean forever. And in addition to that, just as kind of a note, like this is just one notation to describe all the numbers that are possible. You could say all real numbers. You could actually say that. Or you could write this in kind of a fancier script notation, which is basically, it looks like you're writing like a really wide R, then you draw an extra line down, an extra vertical line. That stands for all real numbers. So that would also indicate that it's all of the values that are possible. So just as a heads up, if you want to use kind of the coolest looking notation, I'd say that's in there. And there's actually what's called an alt code for it. I want to say it's alt 2877, but I might be misremembering. Now having said that, let's do the same thing here with our y values. So looking at this, remember we did just make an addition too. Like we could squish this down right off the bat and start to talk about it. But remember just a second ago we said that reading these arrows is actually really important to getting a clean and accurate view of what the y values and x values are possible. So what I'm going to do is I'm going to follow that same pattern. I'm going to extend this down as far as it goes because it's pointing downward, so I'm going to extend downward. And same thing here, I'm going to extend this one downward as well. So basically there is our new version of the graph. It's just a little bit more accurately covering some stuff. And now I want to put this over the y-axis. So as I do this, I'm going to shrink it down to the y-axis, shrink it down to the y-axis. And now looking at our picture, we have a really good piece of information. You'll notice that the lowest value is all the way down here, which indicates that we're going towards -infinity. Once again, these arrows mean that we are continuing downward a lot, so that means we're going to start our interval at -infinity. And in fact, -infinity is just kind of an idea, so we always include soft brackets or open brackets. On the other hand, though, if we look at the top, like the largest y value, notice that we have this peak. It's called a local maximum or a relative maximum, or you might even call it a maximum. It'd be accurate here. That point, we'll call maximum on there, some sort of maximum. That point is the place where the highest y value hits. It never keeps going up. Like those arrows are pointing downward. So that y value would be the highest one we hit. And in fact, I'm going to go ahead and say that that reads to me like 4. So in fact, and because there's literally a point on there, it's actually touching that value, I'll include that. And so by once again kind of squeezing it together, or even just visualizing, you don't need to draw it, and you're probably not going to be able to squeeze your graph together. I don't think that's how these things work. What we've got is a really nice way to see what the domain and the range are for this particular function. And again, fancy method, we're using the projection method. So having said that, I do want to give you a quick opportunity to do a triad. I have a poll ready to go. So I'm just going to project this up. You don't need to do anything particularly fancy with it. But you can imagine at this moment during class, you would be actually like completing the poll. I'm going to go ahead and just write this in there as kind of my placeholder for the amount of time it would take for you to read this graph and figure out its domain and range. Actually, I feel like it's too small myself. Oh, but it's not going to help if I do it here, so whatever. So domain, let's see. Oh yeah, if you're watching this video on replay, like pause the video to go through. So there would be your domain and there would be your range. So nice stuff, but good enough to see. Oh yeah, I should pause. Do you have any questions for me? Chat. Listen for a question. They're all out there. Yes. I think the most common question would be like, why do I include x equals 3? And the answer is that I'm just kind of guessing that it's there. I mean, the dot being present helps a lot. But there's a little bit of guesswork at this point. We don't know for sure. It's not a very nicely drawn graph. Alrighty. In addition to talking about domain and range of a function, there are a couple other properties that we're going to actually look at. Not as fundamentally important, but they're relevant to behavior and being able to describe behavior, which is so essential in later parts of mathematics. So the next thing we talk about is where a function is positive. So in this case, like I'm going to give pretty simple, clean definitions. So as far as like notationally, a function f is positive when, or sorry, a function y equals f of x is positive when those values, the y values, are greater than 0. Oh wait, I should do this right. I'm saying it wrong. Haha, I can fix this. So the positive interval would be all x values with y greater than 0. And of course we could call this y equals f of x, and in fact I probably should, getting caught in the mud here, but where the y values are positive. So as far as graphically, that means that the graph is going to be above the x-axis. So definitely something to be aware of. We're going to be looking for where our graph is actually up above the x-axis itself. We're looking for positive y values. So that's it. And if you're wondering why didn't I just write positive y values, it's because, again, we're trying to be really formal with our definitions. That's part of moving forward in mathematics. Likewise, on the negative one, so let's do this. I'm going to cheat. This is my prerogative as the writer of this thing. Look at how smart this was. So in this case, if we want where the negative interval is going to be, it's going to be when all the y values are less than 0. So in other words, below the x-axis. So there are possibilities here. Now, in looking at this picture, like again, I really like this projection method. I think it's a really mathematically sound way to kind of demonstrate what's there. So I'm going to go through and actually like draw in some stuff on my graph. I'm going to color the parts that are positive, any of the places where the graph is above the y-axis with green. I'm going to color the parts that are below the x-axis with red. In fact, I'm going to go a little bit further and even extend our graph line just to make sure we hit everything. So any arrows need to be considered properly. Means I missed the green one. I should have included that as well. So there we go. Oops. Okay, so there's our graph. I've just kind of extended it so we can see it with the projection method. I want to first figure out the x values where things are positive. As a heads up, when you do this, this isn't one where some are x and some are y. We're talking about the x values. We want to know what all the x values are for which the function is positive. And I should have even included the word positive interval and then negative intervals. So I apologize. I'll be able to fix that in the morning though, or in the afternoon tomorrow, I guess. So we're going to use the x values here. So looking at our picture, actually use the proper colors. Looking at our diagram, we first want to figure out what x values produce positive values of y. Like when is our function above the x-axis? If we want to do the like shrink it down method, actually I can do this I think both. Oops. Boom. Okay, let's shrink this thing down. I'll even bold it. Oh, look at that. That helps a lot. Looking at our picture, it looks very clear to me that we've got a disjunction, by the way. We've got two different like intervals here. We've got one that's running from -3 to -1. And we have one that's running from 2 all the way to the right on the right side, which would be like saying 2 to infinity. We'd include a union in the middle as well. Now, if you're wondering for, like, if something's kind of popped into your head, why didn't I include, like, -1? Why did I use a soft bracket? The reason is, at that point, I'll use -3, in fact. At that point, y is equal to 0, and y is not greater than 0. Like, we're looking for strictly positive and strictly negative. So we need to make sure that we don't include those zeros, because those are neither positive nor negative. So it's going to be a lot of open brackets here. Not always, there will be some times, but these are definitely open. Next, we're going to look at the negative interval. So we're going to do that same thing. Looking at my picture here, like you can kind of figure out, it's basically, it looks like it's everything. Oh no, really? Oh, it's going to try to squeeze it. Oh, it should be okay. So I'm going to squeeze this down. Okay, it's going to, of course, shrink things down. So ignore this for a second. That didn't cooperate the way I wanted it to, but it was enough for us to see it now. The red seems to have disappeared. Okay, let me try this one more time. These are all valuable, like, failures on my part. Oh, come on, really? Let's see if this does anything. Yes, there we go. Okay. So it did... Are you kidding me? Okay, so there's one spot. What? I'm getting caught in the weeds here. Just ignore it. And then we'll go right down here. Okay, looking at our picture, once again, our picture indicates, like just from inspection, that we're going to have two separate pieces, so we'll have a disjunction once more. We'll run from negative infinity to, it looks like negative 3, and we'll run from negative 1 to 2. And that covers our entire setup. Along those same lines, if you're curious, I have kind of a nicer diagram prepared here if you want to see kind of another example of this. But again, you've done this a lot before, so I'm not overly concerned that you'll be able to do it. I'm confident that you can. Do you have any questions for me? Obviously you don't because there's no one here, but this would be a good pause place. Likewise, we could talk about increasing and decreasing intervals. Once again, what I need are intervals. The word's still here. Head of the game. So the increasing interval and the decreasing interval. Valuable pieces both. I think I should probably just have the definitions ready here so I can talk more than write, but we'll see what happens. So the increasing intervals, these will be the places where the following is true. So for a function f of x, and again we're talking about some sort of function that's being described here, f of x sub 2 is greater than f of x sub 1 if x sub 1 is less than x sub 2. So in other words, what we're saying is that, let's make sure I do this better. I'll write this as a translation. Y values get bigger as x values get bigger. And again, like you can kind of tell, like the first definition, you can kind of tell which one's a more formal definition because it looks a little bit more precise. But in the same time, this conceptual definition is really accurate. It's saying that as we get larger and larger x values along the way, we're looking for y values to continue getting larger and larger. And this inequality means that we're literally comparing x value or y values. We're comparing the previous y value to the next y value. So for instance, on this picture over on the right side, which is I left too large, we can see that if we go from here to here, the x values are obviously getting bigger. We're moving in the x direction this way, and as we do, our y values get bigger, which means that we are, in fact, increasing on that interval. And this is actually a huge concept in calculus. It's one of the big ideas that's out there, including formal definitions using a different tool. But for now, we're just kind of interested in what's here. Likewise, we can define the decreasing interval. It's going to be, let's make sure I say this correctly, it's going to be when f of x sub 2 is less than f of x sub 1, if x sub 1 is less than x sub 2. So our excuse me. So in this case, like our conceptual definition, again, probably a good working one to go through, but just there. In this case, instead of saying the y values get bigger, we would say that the y values get smaller as the x values get bigger. So, and again, if the y values are getting smaller, that means that we're proceeding downward, which is exactly what decreasing would mean kind of conceptually. Looking over at our illustration, I don't have a perfect picture drawn already, but I think I can probably make this true. So I'm just going to randomly choose colors. Ha 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 ha. Okay, so there's our graph. Sorry, I didn't do a good job of that. We'll also have this guy right here. And then we'll just color the middle section purple. Okay, so in looking at this picture, we want to figure out first where the function is increasing. So we're looking for where the y values are getting larger as the x values get larger. So we're always starting from the left. I think Mr. Shanning often uses kind of like the idea of an ant crawling along a pathway. It's a good way to visualize it. Got some ant walking. Is the ant's path getting steeper or like negative sleep, or is it climbing or falling? I guess is a good way to say it. Looking at this, obviously the purple one is the one place where we are getting larger. So again, I'll imagine projecting it down to the x-axis and kind of imagining what that looks like. And you can tell like this picture didn't do a good job, but we can see where it starts and stops right over there. We'll say that the increasing interval is going to be the x values between, looks like, -3 and 2. Now from here, I will say that in this particular case, it would be acceptable to include closed brackets. Like there are some definitions that include it, but the definition I've provided, which is truly for what's called strictly increasing and strictly decreasing, doesn't say or equal to. So in this case, I would like you to use open brackets. I'd like you to consider that high and low point as being neither increasing nor decreasing. It's just neither one. Like it's just a high point and a low point. It's a momentary pause and now it's there. So we've covered the purple one. Next, I want to look at, let's see if I do this correctly, the orange place, the ones where the graph seems to be going lower. Obviously, if we start on the left, I know there's an arrow pointing upward, but imagine we're proceeding from the left and moving forward. So we're proceeding from this side, and as we do, we can see the y values are getting smaller, then they get bigger for a while, then they get smaller once again, and continue that way for a while. So in this case, we'll have both of these two in place. I'm going to project them down to the x-axis. And when I do, I can see the intervals. You can tell it didn't work perfectly. Like there's some issues here with it translating, but it does a decent job. Once more, we've got the x values, but we're going to have a disjunction this time. We have two separate intervals. We'll go from -infinity to apparently -3, and we'll union that with, it looks like, 2 to infinity. And there are the intervals for which this particular graph or function is increasing and decreasing, respectively. And again, if you put hard brackets on this particular question, I would not mark it wrong, except for the infinities. They don't belong there. But I would not mark it wrong just because like the definition is a little less precise now than it will be in calculus. So do you have any questions for me? No, no questions because I don't exist. Yep, that's it. That's it perfectly. From here, the next question, I just wanted a quick little try it. I've got a poll ready for you. So I want to figure out what is true for this particular function on the interval from 3 to 4. So again, like you'll have time to answer the poll. You're just inspecting what's there. I'm going to go ahead and label it. So if you don't want to see this and you're watching this on your own time, please pause and give yourself a chance to think. But for me, looks like 3 to 4. So looking on this little interval right there, it looks to me like f is negative because the graph is below the x-axis. And it also looks like, though, that f is increasing. So that would be the correct answer to the poll that ideally I'll be using in class. Although it's going to be cutting it pretty tight. Although 12 minutes left is not the worst thing in the world. Okay, so having said that and completed that quick little triad, that completes kind of the pure informational part. But those have all been very basic and hopefully review-oriented questions. I want to kind of show you ways in which you might be pushed a little bit through these things and ask questions that are somewhat less comfortable. So let me demonstrate one of those for you, or at least offer you one of those. So yes, there is a lot of writing here I may before tomorrow. Consider the possibility of typing up this set of questions just so that that's not a portion that you need to worry about necessarily. But having said that, this is a great opportunity for us to analyze and kind of think about things, as well as kind of look at different approaches that we might take. So in this situation, we're basically being given a verbal description of the behavior of a particular function, in this case called g of x. So it says the function g is increasing for x values less than -2 or greater than 5, and decreasing for values in between -2 and 5. So fairly standard stuff. It also says that g is positive for x values less than -4 to infinity, but negative for values of x greater than, did I say that wrong? I said that wrong, sorry. It's positive for x values greater than -4, and it's negative for x values less than or equal to -4. So just kind of interesting stuff to go through there. But yeah, like, oh, I realized what my mistake was. Close enough. So in any event, here's what we got. Here's where we're going to be like moving forward. So in looking at this from this direction, we want to basically find a way to approach, in particular, question A. On what interval is g both positive and increasing? And in order to attack that, it'd be helpful to kind of use a little bit of color to organize the information that we do have already. So first, I noticed that it mentions g being positive. I'm going to go ahead and say that g is positive is going to be our green color. So we're going to talk about those x values that are between -4 and infinity. And in fact, what I'm going to do is I'm going to sketch out a quick little number line here, just because I think this might help us visualize it a little bit. So we've got this number line. Let's see. Make sure I'm looking at the right thing. Yes, looks like I am. So, okay. So we've got positive happening first. It says that's true for -4 to infinity. So I'm going to go ahead and mark this as -4. And then we've got an open dot, and we'll know that this is representing the region over to the right. So it's all the values that are larger than -4. And you can tell, like already, like the fact that this is giving me pause is proving that this can be a little bit tricky to think about. It just doesn't feel very visual, even though we're going to make it that way. Now likewise, we can also talk about the increasing portion. So we want to talk about a function where it's increasing. I think we used increasing in orange. And it says here that our function is increasing for x values smaller than -2 and larger than 5. So I'm going to do the exact same thing that I just did. In fact, I'm going to make sure that I have the exact same looking number line to help us out. You'll see why in a second. I'm going to, of course, change this look a little bit, but I'm going to also make this bright orange for us. Okay. So in looking at this, we now want to talk about the the increasing portion. So this function g is increasing for values smaller than -2. So I'll go from right there. And also for values larger than 5. Well, so far so good. All we've done is kind of illustrate those things out. Now, what we're looking for here is we want to figure, oop, I made a mistake, didn't I? Like I didn't draw these in very good relative position. So if that's -4 up there, -2 would have to be right here. There we go. So having made that improvement, we now have a nice visual. Like we're looking for the places though where both of these properties hold, like where the function g is both positive and increasing. So what you want to kind of do is imagine taking the information from one of these and bringing it down to the other one. So for instance, that's where -4 would be, and we'd be shading this way. And in looking at this, there are actually two different regions, two different intervals where those two intervals overlap. There's one right in the middle here, like I'll describe it right there, and there's an interval over here. So interestingly enough, if we want to talk about the interval on which both properties occur, we can do that by looking at where those two overlap. It's once again called the union of those two, or excuse me, not the union, it's called the intersection of those two. So having said all that, we basically are ready to go and to write out what both of them are. We're going to write out what the union is. And it shows that there are two actual intervals in which this occurs. First, I'll point out that it's all the x values that fall in these intervals. One is between -4 and -2. It appears pretty nicely that it's true. And the other interval is from 5 to infinity. So there are actually two intervals on which this occurs. And the way we attacked that was by trying to sketch out what this looked like using number lines. Just kind of a quick little way to approach this. Now there is a second way. If you prefer instead to think about this as a two-dimensional graph, you could attempt to actually sketch what this function looks like. And so let's try to do that once just for the sake of giving it a shot. So we're looking over here. I'm going to go ahead and label some values for us. We've got -4, we have -2, and we have 5. So the reason I'm labeling those are all the values which things change, either between positive and negative or increasing and decreasing. So having made that mark, I want to now go through and actually try to plot out what this curve is going to look like. And let's see if we can do that. I think we can. So in looking at this, we need to make sure that our graph is negative for all the values that are below -4. So we're going to be negative down here. So I know we can go that this has got to be negative down here. And then it'll be positive over the rest of the time. So that's interesting. It's only going to have 1 0. That's interesting. And then next, we want to make sure that it goes increasing, decreasing. So it goes increasing, decreasing, increasing. So that's sort of our behavior. So following this pattern, I think we got this. We're going to be increasing for a while, up until -2. Then it's going to be decreasing, but we can't go negative. So instead we'll just go decreasing and then start increasing again. So if we do this instead, like hopefully this did a nice job for you. If we approach it in this particular way, we're looking for the places where we are positive and increasing, and we can actually see that just on the graph. That's going to occur from here to here, and also going to occur from here to here. And that matches exactly what we had before. We're going from -4 to -2 and 5 to infinity. So pretty interesting. Our second question uses a vocabulary piece that we haven't used, at least today, although it's one that you've likely seen before. It asks us or mentions that G has one local minimum. And in reality, the word local isn't the important part. It's really the word minimum. And minimum, for our sake, means a low point. So we're looking for one place that is relatively low, meaning it's not necessarily the lowest place, but anywhere that hits a low spot. And if we picture this, a low spot would occur anywhere that looks kind of like this. And in looking at our picture, it's not the greatest diagram that we drew before, but that's going to occur right here. And in fact, I'm going to steal this picture really fast. Let's see if I can get away with it. Yes. Actually, I'm just going to steal the entire thing. That is my last name after all, even if it's spelled wrong or differently. Okay, let's get some color out of the way here. Oops. Okay, so there's our graph that we have. We're looking for a low point. I see that there appears to be a low point right here. So I would go ahead and say that just from looking at the picture, the only low point that I see is at x equals 5. Now, if you were trying to look at this and think about how it is that we could describe this using the information that we have, you could look at this image right here. You'd be able to say that if we want a low point, a minimum is going to happen when the graph goes from decreasing to increasing. And again, I didn't ask you to justify, so you don't have to put this into words. It's just something that's kind of there. But in looking at our picture, we want to go from going down to going up, because that's really what a minimum is, right? A low point would occur when you've decreased a whole bunch, and then you've reached a place at which you can't decrease anymore. And that's exactly what happened right here. At x equals 5, we reached our lowest spot. So kind of nice stuff. Last question we're going to hit here, as I'm seeing that I'm running out of time, but I think I can make it. It's going to be tight tomorrow, though. I'll tell you that much. It asks us which y value would be larger. X equals 6 is y value, or at x equals 10. So in a sense, we're comparing right now the values of g of 6 and comparing it versus g of 10. But again, we haven't used much function notation yet, so I'm not going to stress about the notation. So we want to know which y value would be larger. Well, now that we have this graph, we could obviously just look at the picture and determine it from there. Like, we'd be able to quickly make a determination and decide where those are. But I want to point something else out for us here. I want to point out that both 6 and 10 are both in the same interval. So 6 is a member of the interval from 5 to infinity, and 10 is a member of the interval from 5 to infinity. And the reason I bring this up is because of the information that's present right up here. It says at the top that our function or our graph is increasing for x values between 5 and infinity. So what that means is that on this interval, our function g is increasing. And we know from earlier that that means that our y values are getting bigger. I'll put that even right here. Y values, I was going to say embiggen, but I'm not sure that's actually a word. The y values get bigger. And the reason I bring that up is that tells us all we need to know. If we want to know which one has the larger y value, it would be at the larger x value, because the x values are increasing. That's what increasing means. So in fact, we could therefore say at x equals 6. And if you wanted to, you could say because g is increasing on, let's see, it'd be from 5 to infinity. So there's a good way to do it. Obviously, this might be a different type of question. I might ask this as a multiple choice to kind of save you the awkward description or the awkward writing explanation. But there is a way to, again, kind of ask you to think about what these things actually mean in a slightly deeper way than you have before. So it's very visual, and obviously you have the ability to translate these things into a visual, but it's not necessarily always going to fall in that particular regard. So having said that, according to my clock, I have like 2 minutes left. So just as a quick little recovery, let me just kind of remind you of what we talked about in this lesson. So first, we just talked about how we could convert between interval notation and inequalities, or in particular inequalities and interval notation, talking about the open and closed brackets, also known sometimes as soft or hard brackets. We talked about disjunctions and conjunctions, although those terminologies aren't needed. We talked about open and closed intervals, and we demonstrated a couple different options, including kind of the weirdness of what happens if it's not really even an inequality. After that, we talked about the function properties of domain and range, basically the input values that are possible and the x value or the output values that are possible. And we use this system that I called the projection method of imagining kind of crushing it down into the number line to analyze what x and y values are actually showing up on our graph. Along that way, we talked about the importance of interpreting arrows correctly and understanding that they mean to continue going in that direction all the way. There will be some exceptions to where they don't grow in both directions, but we won't talk about those ones until later. So we saw a couple different examples and a triad. We also talked about the positive and negative intervals, as well as increasing and decreasing intervals, places where the function is either above or below the x-axis, or getting larger or smaller y values as the x values increase, respectively. And then finally, we ended with a strong verbal problem, one that kind of represents the level of challenge that'll be in there. And what we saw was the best strategy was most definitely to sketch a graph, and in whether it was a one-dimensional or a two-dimensional number line or a two-dimensional graph of a function, all of those options served us pretty well. So having said that, in the final 20 minutes, I would give you the opportunity to work through one or both of the triads that are available. And just obviously, I can go back through problems. I can work through another example of anything that you'd like me to. Or you can get a head start on the problem set, which should be posted in Google Drive. In any event, thank you for watching this. If you're watching this, it means you probably wanted to kind of see it again. I've gotten the information I need, which is that this is barely going to fit into the period, but that's going to be true a lot this entire year, so I'll just do the best that I possibly can. As always, thank you for watching, and have a good night.